So for this video, we're just going to run through this Mathematica worksheet on numerical approximation of integrals. You're encouraged to download the Mathematica worksheet so you can play around with this as well. It should help you visualize what's going on with left-hand and right-hand sums, as well as midpoint, trapezoid rule sums, and then do some calculations with Simpson's rule as well. So I put the instructions in here so you can kind of read through it even if you don't watch any more of this video, but let's just go ahead and go through, kind of see what each of these things is doing. So I've put the commands here, these functions in here for you. You don't have to worry about those. All you have to do is put your cursor in there anywhere and then hit Shift Enter so that Mathematica loads that command. You can get rid of this little thing. And now we can use the command. So we type write Riemann sum plot. And this first entry is our function, which we're going to take to be x squared. We'll take the interval from -2 to 2 and 25 rectangles. So you can change any of these things you like. So suppose we just wanted to do 15 rectangles instead. So you just hit Shift Enter, and this gives us a right Riemann sum with 15 rectangles. So it can kind of help you visualize what's going on. We can change the edges if we like. So it looks like this. Play around with it however you want. You can change your function if you want as well. So see, now we have something like this. So this gives us a way to play around and visualize. If we want to, see if we want to put a bunch of rectangles in there, so like, let's say 50 of them. You see it's starting to become a better and better approximation. We'll see kind of an illustration of this better below, but supposing we put 500 in there, it looks like it gives you pretty much the entire area at this point. So that's how we play around with the visualization for a right Riemann sum. Of course, we can do the same thing with the left one. So Shift Enter to get that loaded. And now we have the same thing, same function, x squared, going from -2 to 2, 15 rectangles here. So you can see each one of them touches on the left edge of the rectangle like we expect for a Riemann sum. I'm just going to up the numbers here a little bit so you can see kind of how it's filling in. It gets to be a smaller over approximation on the decreasing part and a little bit less of an under approximation on the increasing part. So those two commands allow us to help plot and see the different Riemann sums, which you can see with the plot here at the end of it to help you distinguish between the two. We can also just do the calculations of the Riemann sum. So if we want to write Riemann sum here, so in this case it's write Riemann sum. Notice there's no plot with it because we're not going to plot anything. We're just going to do the actual calculation. So again, we're doing x squared from -2 to 2 and 200 rectangles. And that gives us this value. If you want more rectangles, you can just put more rectangles in. So it just gives you a more accurate answer. And it spits this out pretty quickly because it's a pretty easy function to evaluate here. So suppose we wanted to do the same thing with the function e to the x with the interval from 0 to 10 with 15 rectangles. So notice exponential function, 0 to 10, 15 rectangles. So notice if we do this though, this gives us the exact value of this Riemann sum, which maybe isn't what we're looking for. We might actually just want the decimal approximation to that. So if we want the decimal approximation, we go ahead and put this command, write Riemann sum here, and we put an n brackets, put the command and then another brackets to close it. And so let's change this so we see how it evaluates. And so now this is basically the n is telling Mathematica to give us a numerical approximation. So there's our numerical approximation to it. So if you're looking for a decimal approximation, like even up here where we had the fraction, if you wanted that to be in a decimal, just put n and then the command inside the brackets there. Of course, we can do the exact same thing with a left Riemann sum and get the value here. So we can even put this up to a bunch of rectangles and it still spits it out quite quickly. Now, the idea to help us kind of understand how these things fill in the area under the curve here, we'll make a graph where we can manipulate the number of rectangles. So we see here we're doing write Riemann sum plot, and then we have this manipulate to kind of indicate that we're going to allow us to manipulate things. So we'll look at the function x squared on the interval from -2 to 2. We use between 5 and 50 rectangles here. So notice, so let's go ahead and enter this. So we have the function as the first entry, and then -2 to 2, that's giving us our interval there. the next term here, 5, that's the minimum number of rectangles our graph will show, and the second one is the maximum amount. And so now we can see we start here with 5 rectangles, and as we drag this over, it increases the number of rectangles, so we can kind of see how this is filling in as we go. And if we up this number a bit, so let's go up to 500 instead, this really lets us see how it fills in. So we can see, okay, we're filling these in pretty good, and now as we're getting up here with hundreds of these, you can see it's starting to just fill everything in, so that you're getting closer and closer to the exact area under the curve. So it's not going to be the exact area for any particular number of rectangles, but it will get closer and closer with the number we have. Of course, we can do the exact same thing with the left Riemann sum. So let's do this. Let's maybe change our function a bit here from the one that we started with. So let's talk about, say, exponential function. And let's go from, say, 0 to 12 and go 5 to 500. And so now we can kind of see this goes very steep. So we can see, again, this is going to fill everything in here. Okay. So that kind of gives us our visualization and ways to calculate the left and right Riemann sums. So our next thing we'll work on is the midpoint rule. So again, just shift enter this command so it's been entered into Mathematica. And here we'll look at the function cosine of x. Notice we have to capitalize cosine, just like we did with exponential. Our interval here is going to be from minus 2 pi to 2 pi, and this shows us with 10 rectangles here. And so if we want to increase the number of rectangles, of course, just change this. We have more rectangles, and you can continue to change that number. And you can also change the intervals that you're looking on as well, if you like. So we could just go, say, from 0 to 2 pi. And then we just have this part. Or even just from 0 to pi. We have this. So that allows us, the thing to note here is, notice with each rectangle, it's hitting the curve at the midpoint. So this is actually giving us midpoint rule. We also have a command to just evaluate the midpoint. So 0 to pi over 2 with 100 of them. And we put in the n around it because otherwise we're going to get a bunch of sums of cosine values, and we want the numerical approximation. You can see we're pretty close to 1 here. If we had used yet less of them, we're still pretty close to 1, but not as close. So we can see that this gives us pretty good approximation. So if you were to actually evaluate this integral, the integral of cosine of x from 0 to pi over 2 dx, and you use the fundamental theorem of calculus, we would get 1 for this. So it's pretty close approximation. Okay, so if we put, say, 1,000 in there, it's probably not going to be able to tell the difference. Yeah, so you can't even distinguish it from the exact value at that point. We can do another graph with sliders here. So same idea. Here we have x squared from minus 2 to 2, 5 to 100 rectangles. And so just notice if we pull the slider here, we're just filling it in. And notice this fills in pretty quickly to this. Finally, we'll get to trapezoid rule and Simpson's rule as well. So trapezoid rule we'll go ahead and do graphs for. In this case, our function's x squared. We're going from minus 5 to 5 and using 4 trapezoids. We start with a small number here on this picture so that we can actually see the trapezoids. We'll see as I increase that 4, it gets very hard to tell the difference between the trapezoid and the curve in the pictures. So notice our function here is concave up everywhere. And so these trapezoids, these are secant lines, so these are always going to be above the graph for a concave up function. So this is going to give us an over approximation of our graph. So notice here, even if we just change this to, say, 20 trapezoids, it's very hard to see that there's any difference between them. So there is a difference, of course, because this is x squared and these are secant lines. They don't hit exactly, but it's hard to see from the picture. We also have a rule to compute the trapezoid. So we're going to look at the function f of x is equal to sine x squared on the interval from 0 to pi over 4 with 100 trapezoids. The difference with this one from the ones we looked at before is there's no simple antiderivative for sine x squared. So this isn't one we could use fundamental theorem of calculus to evaluate. We have to actually use numerical approximation on this integral. So here, let's go ahead and change this. We'll start off with 10 and see we're 1.578. If we change this to 100, we're 1.571. So it's actually a pretty good approximation right from the start with only 10 trapezoids. This is one of the benefits of using midpoint, trapezoid, and then Simpson's rule over left and right hand sums is even though any of those rules will converge to the exact area if you let there be enough subdivisions of your interval, these ones, trapezoid, midpoint, and Simpson's converge much faster. So it's better for computations because you have to use less subdivisions of your interval from A to B. And finally, our last one is Simpson's rule. There's no picture here for this. Just remember, instead of secant lines here, we're using quadratics that go through the left edge point, the right edge point, and the midpoint of each subinterval. So go ahead and do this, and then we can just go ahead and evaluate here. So let's start off with, say, 20. And so we get 22,032.9. Now notice if we change this up to 2,000, it really doesn't change a whole lot. So this is pretty accurate right from the start, and we don't need a huge number of rectangles. We can also see this by playing around with functions that we can integrate exactly and then using Simpson's rule and other rules. So this first command here is calculate the exact integral of e to the x from 0 to 10, and then we're going to subtract Simpson's rule approximation from that. So if we start off with, say, 20 subdivisions here, we see, okay, we're off by, the Simpson's rule gives an over approximation by about 7.4. If we change this up to 200, now our Simpson's rule is only over approximated by 0.0007. If we change this up to 2,000, now we're already down to 7.6 times 10 to the minus 8. So this is extremely accurate. On the other hand, if we do the same thing where we use a left-hand sum, let's start with 20. We're off by 5,000 with 20. So let's go through and kind of do both of them at the same time to see the accuracy. So for this one, we were only off by 7.4. This one, we're off by 5,000. Notice Simpson's rule is giving us an over approximation. Since this is an increasing function, left-hand Riemann sum gives us an under approximation. So let's change them both to 200. Well, first, before we even change that one to 200, let's change this to 200. So notice even as we change this to 200, it's still much less accurate than Simpson's rule with only 20. Let's try 2,000. 2,000 with the left-hand sum is still less accurate than Simpson's rule with 20. Let's try 20,000. Finally, we get a little bit more accurate. So notice 20 subdivisions with Simpson's rule is about equivalent to 20,000 with the left-hand Riemann sum. So you can see from this how much better Simpson's rule is for an approximation than a left Riemann sum. Again, they both converge to it if you take to the exact value, if you take the limit as n goes to infinity. But for this one, we have to do 20 calculations. This one, we have to do 20,000 calculations. And if we go even to just 200 on this, we're at 0.007. So let's add another 0 to this. And notice now it's starting to take some time to compute. It didn't give it instantly. It took a second there. So let's try, see if we can do one more. See, now it's taking some time to do the computations because now we're doing 22 million rectangles. So Simpson's rule with 200 was instantaneous. Now, even to try to get even close to this with the left-hand Riemann sum, the computer's still running here to do this. And so it's finally outputted this. Notice we're still not even close to as accurate as it is with Simpson's rule. So this just tells you why we want these different rules isn't because theoretically the other ones converge to something different. They all converge to the same thing theoretically. But in terms of actually doing computations, you can do 200 calculations of this or 2 million, and you'll still be better with 200 with this. So computationally, we wanted to use the methods that are most efficient for getting the best approximation. So again, suggest you download this worksheet, open it up in Mathematica, and go ahead and play around with this to kind of get a feel for what's going on with these different rules and how accurate each of them is.